Okay, just ran a little test. It actually is recording sound now. We got it working. What was wrong with it? Okay, so the rest of the semester we will have up-to-date videos with sound. Sorry, thank you for everybody who let me know that it wasn't working. Okay, so today we're going to learn the last two methods for apportionment. So we've learned three so far: Hamilton's, Jefferson's, and Adams methods. Webster's and Huntington Hill's method are both very similar to Jefferson's and Adams in that they are modified divisor methods, which, yes, is tedious. Which is why I'm introducing you to Excel in this project, so you can learn the power of Excel to help you avoid tedium, right? Let Excel do all that and find the number you're looking for. So speaking of the Excel project, just want to quickly point out that that is due on April 5th. So that's coming up in a few weeks. You can probably, based on what we've covered so far, you could do probably about 60% of it. It's all posted in Moodle under Project 2. There are lots of resources in this folder, including videos with little tutorials about how to do Hamilton's method, how to do Jefferson's method, and then Adams and Webster's method are super similar to Jefferson's. So if you understand that Jefferson's video, you'll be able to do Adams and Webster's as well. And then there's a last video on Huntington Hill. There are template files, so you can look at the formulas in Excel to try to get ideas of how to make your file work. And then the very last file this is Project 2, and that's the actual project. So when you submit this, you don't print it or anything because I need to be able to look at the electronic file to look at all your formulas and stuff. So you will just submit it via email when it's done. All right. So before we start the new methods, does anybody have questions like on homework or previous material that you want to go over? Yeah. Sure. I can pull it up. That's second to last question on the homework. This planets one. Okay. Okay, well, let's go over it. Yep. Okay, so we've got the Interplanetary Federation of Fraternia. So just keep in mind also your numbers in your homework are going to look a little bit different than the numbers in my homework. Everybody's numbers are a little bit different, even though the problem is pretty much the same. All right, so we've got 6 planets, A, B, C, D, E, and F, and the Federation is governed by the Interfraternia Congress. It has 197 seats apportioned among the planets according to their populations. The table gives the planet populations as percentages, okay, of the total population of Fraternia. So this is percentages. One of the easiest ways to deal with percentages is to pretend they're not percentages and just say, assume that there are 100 people who live in Fraternia, right? If there are 100 people who live in Fraternia, 11.35 of them live on planet A. And you have to sort of suspend disbelief a little bit because you can have 0.35 of a person, which is weird. But so if I add a total here, it would be 100 people, right? Okay. So based on these populations, we want to figure out how many seats we're supposed to give to each planet, and we're supposed to use Adams' method. Okay. So typically when we do any of the methods we've learned so far, we start by finding the standard divisor, okay, which is total population divided by the number of seats. So in our case, the total population we're saying is 100 people, right? Or you could just say 100%, right? Divided by the number of seats we're giving out, which is 197. So let's see what this comes out to. 100 divided by 197, and you get 0.5076. Weird standard divisor. Usually our standard divisors are numbers bigger than 1, but it's because we have such a small population here of 100 people. All right, so now we go through and we divide each planet's population by the standard divisor. So I take 11.35 divided by 0.5076, and I get 22.36. So I'm just going to put it down here, and then I'll save that row there for the final answer. All right, 8.05 divided by 0.5076, and I get 15.85. 38.97, 76.77, 29.33, 20.41. I'm going to 2 decimal points. No, just no reason. Because I know the next step is that I'm going to round everything down, so it kind of doesn't really matter, right? How many decimal points I carry at this point. Just sort of a good rule to go by is if you're not told how many decimal points, 2 is usually good. Okay, so this is what we call the standard quota, right? That's exactly how many seats each state should get, or each planet in this case. Next thing is that we're doing Adams method. So with Adams method, how do I round? Up. Yeah, the A points up, right? So this is what we call the upper quota. Just push all the numbers up to the next whole number. So I get 23, 16, 77, 30, 21, 33. And then I got to add those up and see how close I am to 197, giving out 197 seats. So I've got 23 plus 16 plus 77 plus 30 plus 21 plus 33 is 200 seats. Add a total here. All right, so I gave out too many, right? I only have 197 seats to give out. I gave out too many. So when you give out too many seats, this number is too big. How do I change the divisor? Make it bigger. You want to make it bigger. Yeah. Yeah. Yeah, so you want to make it bigger. So the idea is if you divide by a bigger number, your answer will be a little bit smaller, right? So all of your quotas will be a little bit smaller, and then when you round them up, hopefully they'll be a little bit smaller, and they'll add up to 197 and not 200. All right, so now I'm going to come up with what's called a modified quota, and I should write down what I use as my divisor. That way I don't lose track of what I've tried. So 0.5076. So our general rule on how to change that number is by 0.5% for each seat off. So I'm off by 3 seats, so I want to change this by 1.5%. So I do 0.015 times 0.5076. Change it by that little bit. I want to make it bigger by that much. Yeah, let's just make it 0.5 because that's an 0.007. Yeah. Yeah, so let's just make it 0.5. Yeah, plus it's nice, a nice easy round number. Okay, so now I start again. I take each of my original populations, divide by my new divisor. Okay. Again, you don't have to do that 0.5% rule. You can just guess. It might take you longer, but the 0.5% rule isn't guaranteed to work anyways. So 11.35 divided by 1/2, 22.7. Oh wait, no, I wanted to make it bigger, right? I wanted to make my divisor bigger, not smaller. 0.5, yeah. 0.5076. It was 0.076, you said, or something close to that? Oh, 0.0076. 0.515. We'll try that. Okay, sorry. I was expecting, the reason I knew I made a mistake there is because I was expecting this number to be smaller than this number, right? That was the whole idea, is you want these numbers to be a little bit smaller. All right, so 11.35 divided by 0.515. Oops. $22.04. Okay, that makes more sense. 8.05 divided by 0.515, 15.63. $28.91. $20.11. Okay, so then I get my modified upper quota. I round all of these guys up, and I get 23, 16, 76, 29, 21, 32. Add them up, and hope I gave out 197 seats. Oops. I did? Great. 23 plus 16 plus 76. You just looked at how many seats we picked up? Yeah. 197. Very good. Awesome. So this is the answer. This is the final apportionment. Okay, so let's look at our next two methods here. Oh, sorry, yeah? Okay, so historical solution number 4 is Webster's method, named after Daniel Webster, again, a historic figure in American history. So Webster said, well, Jefferson rounds down, Adams rounds up. What if we just round like normal people, right? We'll just use 0.5 as the cutoff, and when it's bigger, we'll round 0.5 or bigger, round up. Less than 0.5, round down. This is Webster's method. It's exactly like Jefferson's and Adams, but standard rounding. Okay. So let's see what happens when I do this with the same problem that we've been doing with all of our apportionment, the Congress of Parador. Okay, so I already have the standard quotas done, And if you forgot how we get there, right, the first thing you always do is start by finding the standard divisor, total population divided by number of seats, right? And in this case, that's 12,500,000 divided by 250 seats, and we get 50,000 as our standard divisor. So that's here, we start by finding our standard quotas, take each state's population and divide by the standard divisor. So that part's already done for us because we've done it several times now. Okay, now Webster's method says round these numbers normally, right? So this one's going to round to 33. 138.72 will round up to 139. 3.08 would round down to 3. So you round to the nearest whole number. So we've got 42, 14, 20. And when we add these up, we hope we've given out exactly 250 seats. So we've got 33 plus 139 plus 3 plus 42 plus 14 plus 20. And we've given out 251 seats, one too many. So you use the exact same rules as with Webster's and Adams. When you give out too many seats, that number is too big. How do you change the divisor? Make it bigger. Yeah. Make D bigger. Right? Because if you divide by a bigger number, all your answers will be a little bit smaller. And that 251, we're hoping to bring down to 250. So we want to change, we're only off by 1 seat, so we only have to change by like 0.5%. So what's 0.5% of 50,000? Let's see, 0.005. That's 0.5% times 50,000 is 250. So I just need to make it bigger by 250. So let's try 50,000, 250. And I got to start again. Go to your original population size, divide by your new divisor. All right, this is going to take a couple minutes. And I get 32.76. Thank you. Do you have the 18.6? Thank you. I really appreciate that. And okay, great. All right, so now I round these all according to standard rounding rules. So I'm going to go 33, 138, 3, 42, 14, 20. And what does that come out to? Add them up. 250. Yay. Okay, so this is my final answer here. So almost the same, right? Nothing really brand new here, just normal rounding. You can use the same little mnemonic that we use to remember how to round, like the J in Jefferson's is kind of like an arrow pointing down. The A in Adams is kind of like an arrow pointing up. And the W in Webster's sometimes points up and sometimes points down. So it's like normal rounding. Okay, so we've studied several historical solutions, 4 actually, proposed by 4 important historical figures in American history. But we're going to conclude with a look at how we do it today. Okay, so this is the Huntington Hill method, and it is the current method we use to apportion the House of Representatives. Also, it's the exact same method that we use to figure out how many electoral votes each state gets in a presidential election. Yes.
Figure out like the population of a state, because like constantly people are dying, and then constantly there's like more people. So
that's such a good question. Yeah, that's the census that they do every 10 years is what they base the state populations on.
Oh, it's every 10 years.
It's every 10 years, so it's not particularly accurate at any given moment in time. Yeah. 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 All right. So in 1929, Congress was really fed up. Congress was really fed up with the controversies that were surrounding apportionment. They were constantly changing the method of apportionment because there were constantly states who were upset about the results of the apportionment, right? Like that state got too many, we didn't get enough, we should have another seat, right? So Congress hired a panel of mathematicians to recommend the correct method, right? They said, just tell us how to do this. And the method suggested by the panel of mathematicians goes by the name Huntington Hill after its two inventors. So that was 1929. Congress didn't actually accept the recommendation until 1941. But when it did, it made Huntington Hill the permanent apportionment method, meaning it's no longer up for debate. We will not change it. That doesn't mean someone couldn't try. It's been challenged. But they made it the permanent apportionment method, and they made it self-executing, which means that Congress doesn't have to approve it every time they want to reapportion the seats, right? So it just happens automatically. And it permanently fixed the number of representatives in the House at 435. So we don't play with that number anymore either. So the Huntington Hill method has stood the test of time so far, but it is constantly being challenged by states that lose a seat under the method. Federal courts so far, including the Supreme Court, have all upheld it. All right, so before we can get into this method, we have to take a little mathematical detour because there's a little piece of the method that requires you to understand this, okay? So the standard way of averaging two numbers is to take the number halfway between them. And the way you typically do that is you add them together and you divide by 2, right? That's the standard way we average two numbers. That average is called the arithmetic mean. And it's the most frequently used kind of average there is, right? But there are other kinds of means as well, other kinds of averages. We have the geometric mean, the harmonic mean, the quadratic mean. They're all different ways of finding the average of two numbers, like what is halfway between two numbers. So the Huntington Hill method employs something called the geometric mean. So the geometric mean of two positive numbers a and b, you calculate by multiplying the two numbers together and then taking the square root. Okay. So for comparison purposes, the arithmetic mean, right, you add the two numbers together and then divide by 2. Okay, so we use multiplication for the geometric as opposed to addition for the arithmetic. So let's just do a quick example. The arithmetic and geometric means of 2 and 8. Okay, so the arithmetic mean, I'm just going to abbreviate AM. You add them together and divide by 2. So that comes out to 10 over 2, which is 5, right? That's the old way of averaging that we've always known, right? But the geometric mean says you multiply them together and then take the square root. So that becomes the square root of 16, which is 4. So you get a slightly different average when you use a geometric mean. All right, let's do one that's doesn't come out quite so pretty. Yes.
What if you have two numbers that like don't have an equal square root? You know what I mean?
Yeah.
Like, the point doesn't.
Yeah. That's what we're going to do in the next example. Okay. Yeah, this one came out nice because 16 was a perfect square number and we could just do the square root in our heads. Yeah. So this next one doesn't come out as nice. Yeah. So the arithmetic mean of 11 and 4, add 11 and 4, divide by 2, you get 15 over 2, which is 7.5, right? But then the geometric mean, you multiply 11 and 4 and then take the square root. So it's the square root of 44. Square root of 4, is 44 a perfect square number? It's just a radical. So we'll just get a decimal on our calculator. So let's see. I think I can do this on here. 44 square root, and I get about 6.6. 6.63. So that's it. You just put it in your calculator and round it. Okay, so the point of this little excursion, right, about learning what a geometric mean is so we can learn the Huntington Hill method of apportionment. So I'm going to start off by saying it works very much like Webster's method and Adams and Jefferson's method, in that it's a modified divisor method. But the rounding works a little bit differently. So Jefferson's was round down, Adams was round up, Webster's was round according to the 0.5 rule. So 0.5 and up, round up, under 0.5, round down. So the Huntington Hill rounding rule is different than any kind of rounding method you've ever seen. It's going to take a little getting used to, but it's not that crazy. It says if the modified quota is below the geometric mean of the lower and the upper quotas, round down. If it's bigger than the geometric mean, round up. So for example, let's say a modified quota is 32.68. We have to decide whether to round down or round up. So first, you get the lower quota and the upper quota, 32 and 33. That's the lower quota and the upper quota, the round down and the round up. Find the geometric mean of the two, right? So the geometric mean of 32 and 33 says you multiply them together and then take the square root, and you get 32.496. And that's the geometric mean of 32 and 33. 32.68, is that less than or greater than the geometric mean? It's bigger, yeah, so we say it's greater than. And when we're bigger than the geometric mean, round up. It's greater than 32.496, so we round up. So this is like my new cutoff. Instead of using 32.5 as the cutoff, we're now going to use 32.496. So it's very close to using Webster's method, right? Webster uses 32.5 as the cutoff. Huntington Hill uses 32.496. If you're bigger than that, round up. Smaller than that, round down. Okay, it's weird. It's weird, and it'll take a couple of times for you to wrap your brain around it. So let's do a couple more. Let's say a state's modified quota is 5.48. If I were to round this normally, what would I get? 5. I would round down because 0.48 is smaller than 0.5. I'd round down. So for the normal rounding rule, I'd get 5. But for Huntington Hill rounding, I have to do a little bit of work to figure out which way to go. Okay. So first, I have to figure out the cutoff. It's not always 0.5. Right? So my cutoff of whether to round up or down is the geometric mean of 5 and 6. Okay, so let's figure out the geometric mean of 5 and 6. You multiply them together and then square root. So my cutoff is 5.477. Is that above, right? Is 5.48 above this cutoff or below? 5.48 is bigger than the cutoff, right? So let's write down the cutoff for rounding is 5.477. Okay. When you're below that, round down. Above that, round up. So my number 5.48 is bigger than that, so I should round up to 6. It's weird, right? Right, that number you bring out of the calculator, the cutoff, keep a bunch of decimals. Yeah, because you might need to go pretty far out to compare it. Yeah. All right, let's do another one, right? So we have a state's modified quota is 7.49. This is the number we have to decide whether we're going to round it up or down. So let's do normal rounding first, right? 7.49, which way would we go? Down to 7, because 0.49 is less than 5, right? Yep. All right, but then according to Huntington Hill, I have to calculate the cutoff. It's no longer 7.5. It's going to be the geometric mean of 7 and 8. So I multiply 7 times 8. I square root it, and my cutoff is 7.4833. No, you do 7 times 8, the lower quota times the upper quota. Yep. Yep. So if my cutoff is 7.4833, 7.49 is above that cutoff, so I round up. Okay, so that would get rounded up to 8 in this case. Yeah. No. Nope. The calculator has an algorithm that calculates it. I can't remember it off the top of my head. All right, so the summary of Huntington Hill. Yeah, you're going to need a calculator to be able to do this. Yeah. All right, so the summary. Is this table ready? All right, so my summary is it's the same as the other three methods, right? Find a suitable divisor D. Using D as your divisor, compute the modified quotas. Each state is apportioned its modified quota, but the rounding step is round according to Huntington Hill. Follow the exact same flow chart. If you gave out too few seats, make D smaller. If you gave out too many seats, make D bigger, and start again. All right, so let's do the same example. Congress of Parador. I already have the standard quotas, and I added a bunch of stuff in here to help us with the rounding. Okay, so I need the lower quota and the upper quota to get the geometric mean to figure out my cutoffs. Okay, so my lower quota for 32.92, my lower quota is 32, upper is 33. Then I have 138, 139, 3 and 4, 41 and 42, 13 and 14, 19 and 20. Take the geometric mean of each of the lower quotas and upper quotas, which means multiply them together and square root. Okay, so 32 times 33, square root it, and I get 32.496. Keep a bunch of decimals. You might even want to go a little further than that because we're going to have to compare our standard quotas to these cutoffs. You might need to go out to several decimal places to be able to see which one's bigger. All right, 138 times 139, square root. I get 138.499 is my cutoff. 3 times 4, 3.464. So all my standard quotas just have 1 or 2 decimals. So if I do 3 for my cutoffs, that should be enough. 41 times 42 square root 41.49699. I didn't want to round the third decimal place because I might have to compare it. Yeah. All right, 13 times 14 square root, and I get 13.4907. All right, one more, 19 times 20 square root. Okay, so now my Huntington Hill rounding step is I have to compare my standard quota to my cutoff, right? If the standard quota is bigger than the cutoff, round up, smaller than the cutoff, round down. So 32.92, it's bigger than the cutoff of 32.496, so round up, 33. 138.72, compare it to 138.499. Which way should I round? Up. 3.08 compared to 3.464 cutoff. Which way do I round? Down. 41.82 compared to a cutoff for rounding of 41.49. Up. 13.7 compared to a cutoff of 13.49. Up. And 19.76 compared to a cutoff of 19.49. Up. Okay, add those up. Let's cross our fingers that we're at 250. $251. Okay, so we have to change our divisor. And our divisor before was 50,000. I'm off by 1 seat, so I'm going to change it a little bit. Do I need to make it bigger or smaller? Bigger. So let's do what we did before, 50,250. It worked before when we were off by 1 seat. Let's try it again. So I have to take each state's population and divide by 50,250 now. This is the Huntington Hill method. Yeah, this is the method that is currently used. Yeah. That is a great observation. Remind me when we're done to talk about that. What am I doing? Sorry. 6936. I think I must have left off the 0. That's probably 13.05. You didn't get that? What did you get? 13.63. Okay, thanks. I knew it was wrong. I didn't want to redo it. 13.63. Okay. All right, good. All right, so we got that. And so now I have to get modified lower quotas, modified upper quotas, and the new cutoffs for the geometric mean. So I've got 32, 33 for lower and upper, 138, 139, 3 and 4, 41, 42, 13, 14, 19, and 20. So all my lower and upper quotas are the same. None of them have changed, right? So my geometric means should be the same. So rather than put them all in the calculator again, I'm just going to copy them down. Put another color. 32.496, 138.499. I really hope this divisor works. I don't want to do it again. Okay, so now I'm going to compare my modified quota to my cutoff and decide how to round. Okay. So in this first one, 32.75, should I round it up or down? Up. 138.03, up or down? Down 138. 3.06. Up or down? Down. It's less than the cutoff, it goes down. Yeah. All right, 41.611. Up. 13.63. Up. And 19.66. Up. So when I add those up, what do I get? 250. Great. Good, it worked. So this is my final answer. Okay, and what Elliot pointed out a minute ago is that that is the exact answer we got for Webster's method. Right? We got 33, 138, 3, 42, 14, 20. We used the same divisor, right? It was so similar to Webster's method. And that's because, look at the cutoffs, right? The cutoffs are all really close to 0.5, right? The cutoffs are 0.496, 0.499, 0.464. I mean, that's off by a few hundredths, but it's still really close to 0.5. 0.496, 0.49, 0.4936. So the cutoffs in Huntington Hill are typically really, really close to the 0.5 cutoff you use in Webster's. So it's a really, really, really similar method that's just more tedious. Okay.
So why don't they just use Webster's?
Yeah, good question.
Like, is there like an example where they don't get?
Yes, we can if we're like really careful about choosing our numbers, we can create an example where they don't come out the same. But more often than not, they come out the same. Like almost all the time, they're the same. They're all very frequently the same. Same results. So the question is, like Caroline just asked, why don't we just use Webster's? It's so much easier. Why do you think we use Huntington Hill? They're so similar. They almost always give the same results. Webster's way easier. Any ideas? That's a good theory, that someone is getting an advantage and they don't want to lose it and we just haven't seen it yet. Right, because we move that cutoff down just a little bit, so states with smaller numbers might benefit. Yeah. Any other thoughts? Yeah, there's something to the fact that this is a little more complicated, that sometimes people think math is supposed to be complicated, and they hired a panel of mathematicians. I mean, they couldn't very well come back and say, like, you lay people were doing it right already, you know? Right? So maybe that's why. I don't really know. I don't know, but okay. I kind of want to have you guys do this instead of me. I'm tired of talking. All right, so I would like you to apportion this using Huntington Hill.